Next, we're going to show a couple more examples on how to calculate the power of a one proportion z-test. The third example, following on the first two from the previous video, we're going to assume in this case that everything is the same as in example 1. P naught is 0.4, the alternative is one-sided, sample size is still 100, but we're making a change to the level of significance. It's now going to be 0.01 instead of 0.05, and we're going to use the same true value of the alternative, 0.44. Okay? Now what we're looking at here is if we're going to reject the null hypothesis, we're going to have to get a p-hat that's pretty far out in the tail of this distribution. In fact, it's going to be somewhere past the 99th percentile of all the p-hats. Otherwise, our p-value is going to be bigger than alpha and we would fail to reject. Okay? Now, this 99th percentile from a normal distribution corresponds to a z-score or a z-statistic of 2.3263. If we get a z-statistic from our test that's bigger than this, then we would reject the null hypothesis. And if we don't get a z-statistic bigger than this, we would fail to reject. Okay? Now we're interested in calculating the power, so we want to find the probability basically of getting a z-statistic this big or bigger that would allow us to reject the null. Okay? Now I'm going to reject the null if we get a z-statistic that's bigger than 2.3263. And to figure out what value of p-hat corresponds to that, I'm going to basically unstandardize. I'm going to take my z-statistic, plug in all the values from p naught and n, and then figure out what p-hat has to be in order to satisfy this inequality. Well, those values of p-hat would be anything that's greater than 0.5140. See, I took the mean plus the standard deviation times the z, and I got that. So basically, I took this standardized z and I unstandardized it to get p-hat, so I'm working backwards. So this is basically a two-step process. We worked backwards to get from the 99th percentile to the z, and then we worked backwards from the z to the p-hat. So anytime we get a p-hat that's bigger than 0.5140, we'll reject the null hypothesis. Now the probability of getting a p-hat like that is the power of the test. We're going to assume now that the truth is 0.44 for the true p. Subtract the mean, divide by the standard deviation on both sides. We can use 0.44 in here for the mean and in here, and 1 minus 0.44 in here, and then sample size. And when we calculate this, anytime we get a z that's bigger than 1.4908 under this calculation, we would reject the null. That's only going to happen about 6.8% of the time. So that shows you that if you reduce your alpha level, that's going to reduce the power of your test, other things equal. And that's something to think about. When you choose your alpha, you have to balance out the probabilities of type 1 errors and type 2 errors. If you want to reduce the probability of a type 1 error, you would make your alpha smaller so that it's harder to reject the null. But at the same time, you're going to increase the probability of a type 2 error and reduce the power of your test. So always be aware of that trade-off. Next, we're going to look at a fourth example, and this one is based on the same original information that we had, except now we're changing the sample size from 100 to 900, and then at the end we'll see what happens when we change the sample size like that. Okay? Now we're going to reject the null hypothesis if we get a z statistic bigger than 1.6449, same as in the first example and the second example. And then the z-score, the p-hat that we would need to get in order to reject, we can get by doing this calculation. You notice with the sample size being different, the standard deviation is going to be a lot less than it was in example 1. And p-hat is going to be, anytime we get a p-hat bigger than 0.4269, we would reject the null. Okay, so again, what I did was I went from the 99th percentile to this value of z, and I unstandardized to get these values of p-hat. It would cause me to reject. So I'm going backwards using what I know about normal distributions. And now I'm going to go forwards. I'm going to calculate the probability of getting a p-hat bigger than 0.4269 if the true p is 0.44. To find that, you standardize, and you're going to reject if you get a z that's bigger than negative 0.7917. And the probability of that happening is 0.7857, almost 80%. So what happened was we took a situation where we had a sample size of 100 and our power was about 20%, and then we increased our sample size to 900, and our power went up to almost 80%. So that just shows you, if you increase the sample size, that increases the power of your test, and it reduces the probability of making a type 2 error.